Hi folks, Mr. Long here. We're going to do some graphing of logarithms. Just really quickly, let's take a look at what our basic log curve looks like. So we know that it's like this. We know the exponent is on the y-axis and the evaluated power is on the x-axis. So in this case, what we have x comma y equals the evaluated power, comma, exponent. Okay, comma, exponent. Whoops, looks like a P. Looks like a Q, not a P. Okay, so when we know that point, then it has to be 1 comma 0, because if the evaluated power is 1, the exponent has to be 0. We know that the vertical asymptote is at x equals 0, is the VA, and we know our domain is x is greater than 1, greater than 0 rather, because it isn't possible to repeatedly multiply or divide something and get a negative. Okay, so we're going to do some sketching now. Okay, here's the function we're going to sketch. Y equals 4 log 0.001x plus 0.0005 plus 1. Okay, so let's take a look at this in terms of what we can do. If you remember from grade 11, we would often factor that argument, that's called the argument, everything inside the bracket, or if you think in terms of composition of functions, the inner function, you would factor that to ensure that you can see any features that are related to the horizontal stretch or shift. So let's factor that. So when we factor that, we factor out 0.001, which means we're dividing everything by 0.001. So that becomes x plus, and then we have to go decimal 0005 divided by decimal 001. And we get 2. So plus 1. Whoops, daisy, we don't have a plus 1 there, sorry. Let's erase that. So now I'm going to rewrite this as y equals 4 log 0.001 bracket x plus 2 plus 1. Well, we know from our log rules that log of AB equals log A plus log B, but because multiplication, we say it's commutative, which means the order doesn't matter. We can go log of B plus log of A. So if I'm going to pick B here, that gives me this as B, and this is A here, and then this is going to be A. I can rewrite it as follows on the next page. It's going to equal 4 log x plus 2 plus 4 log decimal 001 plus 1. Well, what is 4 log 0.001? We know that what exponent makes an evaluated power of 10 decimal 001. Pretty sure it's, I'm going to have 4 groups of negative 3 there, plus 1, which is going to be minus 12. So this 4 groups of negative 3 shifts the curve down vertically by 12. So when we rewrite that, we're going to get 4 log x plus 2 minus 11. And now we've got our function in transformation form. So what we need to do now is to get some features. We need to get the x-intercept, the y-intercept, and note the vertical asymptote. So let's do the y-intercept because that's pretty easy. X equals 0 at the y-intercept, and when you sub in that, you're going to get y equals negative 9.8, and then we do the x-intercept, and for the x-intercept we know that y equals 0, and so I end up with 0 equals 4 log x plus 2 minus 11, and then in order to solve this I'm going to have to add 11 and divide by 4, and I'm going to get 2.75 equals log of x plus 2. Well, what's the next inverse operation? By the way, folks, make sure you press pause anytime and rewind to review this. So how am I going to do an inverse operation? Well, what's the inverse of log? Exponents. So when I inverse this, and one of the things that I use for inverse, I'll write down what we've got. 2.75 equals log of x plus 2. For me, the inverse symbol is x, y. That shows I'm doing the inverse. So I would write 10 to the 2.75 equals x plus 2. Now I need to subtract 2, and I get x equals 10 to the 2.75 minus 2. X will equal 560. Wow, that's really far to the right, but I think we're going to understand why in a minute. And then with regards to our domain, we know that x plus 2 must be greater than 0, and we know that because you can't repeatedly multiply anything or repeatedly divide anything and get a negative when your base is positive. In this case, we have a positive base of 10. So in this case, x must be greater than negative 2, and therefore we have a vertical asymptote at x equals negative 2. So I've got my x-intercept, I have my y-intercept, and I have my vertical asymptote. So let's sketch those on the curve. So when I go to sketch this, I'm going to get x equals negative 2. I have a value of negative 9.8 on the y-axis, and I have a value of 560 for the x-axis. And I know it starts here and goes up, and then it continues way far to the right. Okay, and so the question is, this being y and this being x, why do we have these values? Well, on our original curve we had 4 log 0.001 x plus 2 plus 1, which worked out to, if we remember, whoops, this right here, log of 0.001, was worth negative 3, and then multiplying by 4, it's negative 12. So that really is a shift down by negative 12, okay, shifting down by negative 12. And that's why the y-intercept is way down here at negative 9.8. What it also does is it gives it a lot more room that it's growing for before it crosses the x-axis. But there's another consideration as well, and it's related to equivalency. If you look, 0.001 is a coefficient for x. It multiplies into x. Well, we would know that 0.001 represents a horizontal stretch of 1 over 0.001, which is 1,000. So it's stretched horizontally by 1,000, which is why it's way out here. But the interesting part of that is that a horizontal stretch of 1,000, h stretch of 1,000 equals a vertical shift down by 3. Okay, that's really important with logarithms because it comes from our logarithm rules. Okay, for a base 10 logarithm, if we're stretching by a factor of 1,000, if the k value, if you remember, is 0.001, it means we've shifted down by 3. Those are equivalent transformations. for logarithms. Okay, folks, so that's how you graph a logarithm.